Well, CMOS itself stands for complementary metal oxide semiconductor. So it's a recipe for making microelectronic devices, electronic chips, which has become very popular in the last 20 years or so, maybe more. And so almost everything that is a microelectronic chip is made with the CMOS recipe. And then the CMOS image sensor, an image sensor is the electronic film, if you want, in cameras that converts light signals into electrical signals that a computer can understand. And so it's that chip that's at the heart of every camera, basically. So that's a CMOS image sensor.
That's my guest, Dr. Eric Fossum, inventor, entrepreneur, professor of engineering, and associate provost at Dartmouth College. Next on Reliability Matters.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Dr. Eric Fossum is best known for the invention of the CMOS image sensor, better known as the camera on a chip, used in billions of cameras, from smartphones to web cameras to ingestible pill cameras to DSLRs. In 2017, Eric was co-recipient of the Queen Elizabeth Prize for Engineering, the world's top engineering prize, and considered by many as the equivalent to the Nobel Prize, for the invention of digital imaging sensors. He was inducted into the National Inventors Hall of Fame and is a member of the National Academy of Engineering. He is a solid-state image sensor device physicist and engineer, and his career has included academic and government research and entrepreneurial leadership of several startups. He is the John H. Krehbiel Sr. Professor of Emerging Technologies at the Thayer School of Engineering at Dartmouth College. Eric also serves as Associate Provost of Dartmouth College for Entrepreneurship and Technology Transfer and directs Dartmouth's PhD Innovations Program. He recently co-founded another startup with his former students, Gigabot Technology Incorporated. Here's my conversation with Dr. Eric Fossum. Dr. Eric Fossum, welcome to Reliability Matters. Thanks for being my guest today. I really appreciate it.
No, thank you for inviting me. It's my pleasure.
So you and I met. Well, I've seen you before. I remember you. You probably don't remember me, because I've been to some of your some conferences where you've spoken. I've read some of your papers, but you and I actually had the chance to sit down together at a crowded lunch table with some of your students, I believe, and some others in Hawaii about 8,000 years ago in February of this year, and I remember just kind of being that geeky, nerdy kind of guy, kind of gushing over like, I'm sitting next to someone who invented something where there's probably 200 of them in the room at this very moment. I want to talk to you about, the obvious thing, the technology that you produced back in the day, and where it's going, where it is today, where it's going to go tomorrow, and some of the challenges, because I assume there was a few along the way. And I want to talk to you about entrepreneurial stuff, because I know that that is a passion of yours. You are an entrepreneur and an engineer. Sometimes those two don't work well together, but clearly it has in your case. So I kind of want to get into that. So does the fact that your invention changed the world, including people and companies and entire industries, does that still startle you? Do you wake up once in a while and go, that was me?
Yeah, actually it does. I mean, you would think I would be used to it, but now it's become so embedded and so ubiquitous. Most of the time, I don't think about it. But every now and then, there's someone using a camera or something like that, especially if I don't know them, they don't know me. It's like, wow, this is like really weird to like see people using your technology every day, stand next to them. It's like that old American Express commercial. You may not know my name, but you know my technology. And,
right. See, you're a bit more humble than me. I think if I had stumbled across, I say stumble as if you won the lottery, but if I had invented something like that, I would probably be inclined to just tap people on the shoulder and go, hey, that's me. So, well, you're not more like me.
I'm embarrassed to say, but occasionally I'm a goofball and I do that. I remember some couple taking a photograph in Europe, and I said, "Excuse me for a second, can I just photobomb your picture?" And they kind of looked at me, and I had my wife take the picture, and then after it was over, well, they were very polite, but they were like had no clue what I was doing there. They looked around, and I explained to them what it was. They still didn't quite believe me, but then about 2 weeks later, I got a
They
email,
Googled you, I'm sure,
email
right?
from them, and they're like, "Holy cow! I can't believe it. We met."
Yeah, yeah, very good. So before CMOS, well, first, before I even ask you that, for the one person in our audience who has no idea what we're talking about, um, explain to my audience what CMOS is.
Sure. So, well, CMOS itself stands for complementary metal oxide semiconductor. So it's a recipe for making microelectronic devices, electronic chips, which has become very popular in the last 20 years or so, maybe more. And so almost everything that is a microelectronic chip is made with the CMOS recipe, more or less. And then the CMOS image sensor, an image sensor is the electronic film, if you want, in cameras that converts light signals into electrical signals that a computer can understand. And so it's that chip that's at the heart of every camera, basically. So that's a CMOS image sensor.
So before CMOS, I think there were digital cameras. What was the technology used before CMOS?
Another acronym, it was the CCD, better known as the charge coupled device. That was invented in about 1969 at Bell Labs and worked quite well for a number of years, and still in use in some very, very small niche areas, but mostly that CCD has been replaced by CMOS image sensors in nearly all of the 6 billion cameras or something made every year these days. So.
I've always been a video geek. I used to edit family vacation videos, and you never want to come to my house because you'll just get death by video. But I used to set up multiple VCRs, before there was software to do it, and hard edit the stuff. And my prized possession back in the day was a Sony 3 CCD camera, and I might as well have been a CNN crew, with a camera on my shoulder. It was a wonderful camera back in the day. I'm sure if I saw the resolution of it, on it today, by comparison, it would probably not seem so wonderful. So it's been said that the enemy of great is good. So since we had CCD out there, and from my perspective, I thought it was pretty good in the day. What caused you to try and make it better? What led you to the motivation to say, I can do this better? What were the pitfalls and the the technical time, the context of that time that made you think that you could do it better?
Okay, I hope you don't mind a little longer answer, which I think will make it more clear.
Absolutely.
So CCD is a charge coupled device, as I said, and it works by collecting light into the chip, and then it has to do kind of a conveyor belt and move all of that collected signal out to the corner of the chip for readout. So the analogy I like to use is imagine you're trying to measure rainfall across a football field, where the rainfall is actually the light that's falling, and it might vary from place to place. And you want to measure that. So you fill the field with a lot of people with buckets. So they're all standing there holding their bucket, and they collect the rain in the bucket. And now you want to find out what the map is. So you have everybody start passing their bucket of water into the person next to them, kind of bucket brigade style. And then when it gets to the edge of the field, you have another line of people that run down the long length of the field, and they're also transferring the buckets as they come from the edge of the field to the edge of the field, all the way down to the corner. And way down the corner, there's somebody with a measuring stick that's measuring the water in each bucket. And that's kind of a pretty good analogy of how a CCD works. But the problems are, limitations are that if you want to make a more accurate measurement of the football field, you need more people and more buckets, but you still want to do the measurement in the same amount of time, like 30 frames per second if it's a camera. So everybody has to pass their buckets that much faster, right? And that means that the room for error or the chance of losing some water along the way is greatly enhanced. And as you try to improve the technology to make more and more high resolution cameras that might even operate at faster speeds, you just compound this problem of transferring the charge or transferring the water in the buckets greatly. So the approach that we took, which is something called an active pixel sensor, but in this case, it's, imagine you give every person on the field their own measuring stick and a walkie-talkie to call in their results. So they don't have to transfer the water in the buckets all the way to the corner of the field anymore. And so that means that as you try to increase the resolution or the number of measurement points, you don't have that problem of passing the buckets more quickly and more quickly and more quickly without losing anything. Everybody can call in. So that's not a bad analogy. It makes sense.
Yeah, no, it makes a lot of sense. So without CMOS, we would probably not have faster frame rates. You know, right now my iPhone 11, whatever number it is, has way more than 29.97 frames per second, and it shoots 4K video. That, I'm assuming, would probably not be, the buckets don't move fast enough back in that analogy with CCDs for that to happen. Is that correct?
It would be a much more difficult challenge. It would even consume more battery power than those old CCD cameras did, which, you remember, you had to change the battery on those CCD cameras about every 25 minutes or something like that. And they were the size of a brick. They were big batteries. And part of that has to do with the fact that when you're doing the bucket brigade across the field, it takes a lot of electrical energy to make that all happen. So would wear down batteries pretty quickly. So power dissipation is an important part of that problem with going to higher resolution, besides just losing the water along the way.
So were you affiliated with a university when you were working on the CMOS project?
I was, but actually I was working for NASA at the Jet Propulsion Laboratory in Southern California.
In Pasadena, right? That's the
Pasadena. That's part of Caltech. So sort of university, but really it was more like a government job. And at that time when I went there, which was in 1990, they were flying CCDs on the big spacecraft. JPL is responsible for the robotic exploration of space. And so they would send big cameras out to Saturn or Jupiter or our planets, and more recently to Mars. And then these cameras, though, using CCDs were used a lot of power, as we just talked about. And they were very bulky as well. And so, and also part of that was also that they wound up weighing a lot. And of course, mass is very important on spacecraft. You want to reduce the mass because that impacts so many other parameters, including cost, that it's well worth it to reduce the mass. So these CCD cameras in space also had another problem, which is that in space you have a lot of radiation, cosmic radiation, and so you can imagine that it's like shooting holes into these buckets as you're trying to transfer the buckets across the football field. So the stuff is leaking out also, and it's getting worse and worse with time. It's like the CCD electronic device is wearing out over time in exposure to space. So that was another problem. So many problems with CCD. So even though they worked pretty well in your camcorder or other devices on Earth, out in space, they still had a lot of issues. So,
right. So the Hubble, I would assume, has a CCD because of its age.
Yeah, Hubble had a CCD camera. It was 800 by 800 resolution, but it was very carefully designed to try to withstand space radiation for as long as possible. if you tried to put a higher resolution CCD into space, it would start to have the same sort of issues too.
Right. So, considering that CMOS became by all definition, a disruptive force in the industry, did you ever get a call from Kodak, tap you on the shoulder and go, "Hey, Eric, what the hell?"
Well, at that time, most CCDs were for consumer devices were being made in Japan. So the NECs or Matsustas kind of companies. But Kodak was a company in the U.S., maybe the only consumer, maybe Polaroid too, that did CCDs for consumer applications. But I'm the one that called them. I said, hey, we've invented this interesting technology, which they already knew about by that time, just from publications and conferences. But I talked to them and said, look, can we work together and try to transfer this technology out of a government lab into the private sector, because it's paid by taxpayer money. We should try to get some taxpayer return on that investment. And they were quite willing to work with us, and did, and we made further improvements together. But then, unfortunately, Kodak kind of fumbled the ball, as they fumbled a number of things, and so it didn't really go too far in Kodak because of that. In fact, the first CCD self-contained camera was built or invented by my friend Steve Sasson at Kodak back in '75, and they fumbled that as well at Kodak. Decided, hey, that's really interesting, Steve, but go back to the lab and work on something else that's actually useful to our company.
Yeah, I think the lesson of Kodak is probably taught in business schools, and
yeah, I lived it. I mean, it was front and center.
That must have been frustrating because you understood and appreciated the technology of digital photography and digital image capturing, and to see the largest, film producer in the world, with that actually had, they were in the American and the world lexicon, Kodak moment, and these days won't even understand what that means, but to see them fumble something that big is
it's really too bad. Right? They actually at the top level, they understood that they need to go into digital photography. But what I understand from talking to people is that the engineers understood the promise, and senior management understood the promise, but middle management thought they were still a chemical company and kind of resisted changes, which is really too bad. But not uncommon in big companies, and Kodak is just one of many stories one could tell.
Right, inertia is hard to change directions. They know what they know. I look at companies like 3M, that clearly, when you look at what 3M stands for, I don't think they do any of those things anymore. They've evolved. AT&T, we don't have telegraph poles anymore, but they evolved, and Kodak, I guess, just fell on their chemical sword.
Actually, interestingly enough, AT&T Bell Labs, which is where the CCD was invented, they called us at JPL and said, we're still interested in the picture phone. We would still like to do something with that. We think that your technology could help us get there. And so we transferred the technology from JPL, NASA, to AT&T Bell Labs. And actually that went pretty well. But then they had another problem inside. Bell Labs was not the manufacturing part of AT&T. So there had to be another transfer step to a manufacturing arm or product arm of AT&T. And that also did not go so well, kind of like the Kodak story. So actually, we tried to transfer the technology to many different companies, including like Motorola and National Semiconductor, Intel. But there was a lot of resistance to that. People weren't making these kinds of devices anyway. I tried to explain that, look, now that we're using mainstream CMOS, it's possible to build them in the United States and kind of take back the market from Japan. And they were all sort of interested, but they didn't actually do too much. And eventually at some point, myself and some close colleagues said, you know what, if this is going to go anywhere, we need to do it ourselves. And that's we started our own company, spun out from JPL, called Photobit was the name of the company.
Clever name.
Yeah, I wish I could keep using it, but so it was myself, my former wife, Dr. Sabrina Kemeny, Bob Nixon, and Nick Dudamopoulos. Started classically in the basement of my house in California, and then grew from there pretty quickly, actually. And
I love garage and basement stories. I started my company out of my garage, and it's just there's some kind of rite of passage, as opposed to buying a company that's already in existence or something. There's just some, I don't know, you get grit in your soul, from doing that. And if you could pass that stage, you can almost do anything.
Feels that way. It's certainly a lot of fun to think about, especially in retrospect.
Yes.
Not quite as much fun while it's happening.
Yeah, I've burned through a few friends because I all think they're just as interested in my startup story as I am. Usually not, but anyway, it lives in my head. So were you aware back when you were working on CMOS that how much of a disruptive force this would be or could be, or did you just think it was just the next level improvement over something that was already there?
Actually, I was pretty aware that it could be pretty disruptive. And ubiquitous eventually, because we knew that not only would the power dissipation be reduced by 100-fold or something like that, so it could be portable and go to a lot of places. We knew it would also be inexpensive, so fairly cheap camera, small camera that could last for a long time on a battery. It was lots of possibilities, and in starting Photobit, we had recognized that not only is it good for space, but it's good down here on Earth as well. And there are a lot of things I thought about that actually wound up coming true, remarkably. I remember being interviewed by BBC Radio. Some guy came to my lab at JPL and wound up talking about, could these be useful on the bumpers of cars, and would cars like be able to use them? And it's like, yeah, definitely, it's what we'd like to do, among other things. And today they're ubiquitous on cars for backup cameras, right? I mean,
yeah. Well, my rear view mirror, up here is a screen, and it's the best rear view mirror I've ever had, because I could have all these obstacles between the mirror and the back window, and it doesn't matter. I'm looking from a camera, a wide angle camera. I can adjust how much of a wide angle I can adjust zoom and all that stuff. Are there any? You had quite a bit of vision. You were aware, as you said, that this thing could be big, and
but by the way, I didn't really believe it would ever get there. I knew it.
There's a difference between what the possibilities are and the road to get there, right? I get that. Yeah, if this thing makes it, it'll be big, rather than this will definitely make it. Yeah, there's all these obstacles. We're going to talk about the obstacles in just a second. But looking at it today, are there any surprises with uses or unintended uses of this technology that you think is good or not good, or
oh my gosh,
has it taken any turns?
Yeah. Oh, I love talking about this kind of topic. So, for example, who didn't foresee the rise of a company like Facebook or Instagram that basically traded in digital images online? And that's become a huge company and a huge factor in even in U.S. elections and other things. So had no idea that industry would pop out as a consequence of people having so many cameras at their disposal. Another one is that I did know was going to be an issue is kind of privacy versus security. So let's talk about like the Boston Marathon bombing, where we caught those perpetrators very quickly And part of the reason we were able to catch them quickly is because there were so many cameras around that people caught images accidentally of them, and the police were able to string together all these things and find out who they were and then track them down. And I personally, I don't like the idea of like being under surveillance all the time. So many cameras watching us all the time. Not very proud of that particular thing. But when it comes down to the security issue of like catching bad guys, then I feel good. So I'm always torn. It's kind of the yin and the yang of the new technology.
I think if you were to put pros and cons on a scale, the scale would be very one-sided to pros. Just the fact that this technology has allowed us to connect the world.
Oh yeah.
In overwhelmingly positive ways.
Well, look, even right now, we're using the technology you and I to communicate right. with your audience. I get to talk to my 85-year-old mother in video chats. She's kind of isolated in her house because of the pandemic. And my daughters can join from different parts of the country, along with her great-granddaughter. And we can all get together for Sunday afternoon chats. Wow. I mean,
yeah.
Right technology at the right time.
Yeah. Sorry. So much good over. I think there's more good use than misuse.
But there's one thing I feel particularly proud about, very, very happy with, and that is, which I didn't expect at all, no clue, but it has to do with social justice. That having all these people armed with cameras in their pocket, they're able to catch very unpleasant situations, criminal situations on camera, which just makes all the difference in when it gets down to your word versus my word, if you've got the video recording of it. And it's really, I think, changed the world in a lot of ways. It's still changing the world in a lot of ways.
I think we're in the midst of it right now. I don't think things are worse or better. I think things are now understood more. I think things have been happening for a long time that we just didn't know until we have 320 million reporters in one country, right?
So,
and I know I would act different if I was in an argument with a retail establishment or something. If I had bad service at a restaurant and I saw a camera pointed at my table, I would certainly censor myself more than I might if I thought nobody was watching except for, the two parties involved. So,
right.
Yeah, that is a good takeaway from that. So let's talk about challenges. I'm an entrepreneur. You're an entrepreneur. Our industry is built from entrepreneurs, and things don't come easy. Most people don't realize the vastness of the challenges that we all face. I want to get into the technical challenges in a second, but before we do that, what were some of the non-technical challenges you faced? What was there pushback from industry or other forces? What did you have to overcome outside of the technical side?
Yeah, everything. So there was CCDs were entrenched. They were in camcorders, and Japan was producing great CCDs at volumes that today seem small, but at the time it seemed pretty significant, millions, per month perhaps. It was very entrenched. Everybody I knew, every technologist in imaging, were making CCDs, right, or working on CCD technology. And here I was all of a sudden telling them that, hey guys, actually the CMOS image sensors are the next big thing. Pay attention. They didn't want to hear about that because that would threaten their job, right? So it's always a trouble with a disruptive technology versus some entrenched technology, is that everybody is threatened. Everybody all the way down the food chain is threatened. So there's a resistance to the new technology, and you have to prove that it's compelling because otherwise people wouldn't change. So making the case for it being a compelling technology was a challenge. Actually, people outside of, let's call it the camera ecosystem understood it much better. In fact, I was just talking to a group at Stanford. I just gave a talk at Stanford a couple of weeks ago, and they were reminding me that after their academic group had heard about the CMOS image sensor, they were fully on board with the fact that it was going to take over. And in fact, they were working with Hewlett-Packard and other companies in the Bay Area also to try to come up to speed. So we had like this two things. We had this like big obstacle of what would be our customers and my colleagues around the world, professional colleagues, kind of putting up a lot of resistance. At the same time, we had people that got it, starting companies to compete with us. So it was kind of a double whammy of like, wait, one of these ought to be true. But in retrospect, as an entrepreneur, you don't like to hear about your competitors coming to market. And for example, the first company that really entered the mainstream market in a big way, I mean, we were in it as Photobit. We were building chips for Intel's webcam and Logitech's webcam. But Toshiba came into the marketplace as a semiconductor chip manufacturer. And our first thought was, oh my God, we're dead. How can we compete against a company like Toshiba? But what we found, interestingly enough, is that a company like Toshiba coming into the marketplace gave the technology a lot of credibility. All of a sudden, people woke up and said, oh, this must be real if Toshiba's investing in it, is entering. Right. And the other thing that I didn't appreciate as much at the time is, as a small technology company, you can be very nimble. You can move very fast, whereas the bigger players like a Toshiba or a Sony or a Samsung are much slower to the marketplace. But they're also like elephants, and eventually they will crush you, which now Sony and Samsung are the big players in the world. But at the beginning, that competition can help a small company a lot.
Yeah, I agree. I think the auto industry, you have Tesla, who's kind of like you were, a compelling force, just driving a technology forward at record pace. But I think the other, the mainstream, the big three or four, whatever they are sitting back on their perches, kind of looking down, waiting to capitalize on that market. And I'm sure that happened in your industry too. The Toshibas of the world, or others, probably sat back and said, "What's this guy doing?" And waited for you to overcome some obstacles and clear a path for them, and then, boom, they just pounce. Did that happen?
You do, as they say, you don't have to be first. You just have to be the last person standing, right?
That's correct. That's correct. And that's almost a wise business strategy. Let the pioneer go out and blood, sweat, and tear it, and then say, thank you very much. We'll take it from here. Now, was CMOS a patentable item? Or what was the status of protection?
Yeah, so the initial IP that was developed at JPL, which is part of Caltech, that IP is all owned by Caltech. And when we spun out Photobit, we actually had to first get a license from Caltech. We got an exclusive license from Caltech. In fact, Photobit was the first company being spun out of JPL, or that spun out of JPL, that was able to license their own technology from Caltech. Because up to that point, Caltech was extremely conservative about that. They didn't want to look like they were favoring their own employees or something like that, which is kind of ancient thinking these days. But at the time,
I would think they would want to reward the person who handed them a very valuable patent.
Well, in their mind, they're like, oh, well, we're happy to license Kodak or somebody, but why would we license it to one of our own employees? It sounds like we're taking this government money and then we're letting inventors run away with it.
Ironically, optics probably got in the way.
Yeah. So of course, especially after Bayh-Dole Act and other things, even the government wakes up to the fact that it's much better to not own the patent or sit on the patent. It's better to let the inventors run with it, license it from the university, for example. So, and then of course at Photobit, we probably invented another 100 patentable things that were patented. in the process. So the patent wall was kind of, well, there were patents, but there was no wall, right? It was a very heady time. A lot of other companies jumping into it and grew very quickly. And the patents take a long time to issue, as you probably know. So people don't know what you've patented or not patented.
Right.
But years later, Caltech kind of woke up and said, "Oh wow, all these people are making a lot of money off of our IP," and so they enforced their patents, and they did very well in that process. I'm sure they were to build a number of buildings at Caltech if you were to monetize it that way. But anyway, so they did well. Yeah.
What were some of the technical challenges? I feel free to go deep if you want to. I'm sure we could talk about that for a month, I'm sure. But what were some of the bullet point technical challenges that maybe you didn't foresee going in, or maybe you did foresee going in that you had to overcome?
Well, the first technical challenge was more of an ecosystem challenge because CCDs were made in Japan. So things like color filters on chips and micro lenses on chips and some of the other back-end processing that you'd have to do to the wafers was not something that anybody really knew well in the US, not even Kodak, because they had their own kind of CCD line. So how to integrate all that with modern CMOS was an obstacle for us because we had to figure it out and teach it to the foundries that we use, the manufacturers of semiconductors. I guess I should back up and just say most small companies don't build their own chips in their own manufacturing line. We send blueprints to a large semiconductor manufacturing company that all it does is manufacture semiconductor chips from blueprints. It's called a foundry. And then they send the chips back to the company after they're fabricated. Of course, there's a lot of back and forth communications, but it's called a fabless operation, fabless semiconductor company. So we had to teach those foundries a lot of stuff, or learn with them a lot of things too. So that was one challenge. And then there were lots of other challenges because now with CMOS, and one of the reasons for going to CMOS overseas is that we could integrate a lot of other electronics on chip. So we got rid of that big bucket brigade thing, which is the heart of the CCD, and figured out how to make a good image sensor or good pixels out of CMOS. But then once we were using CMOS, we could integrate all kinds of other electronics on the chip, like converting it to digital signals, analog signal processing, and timing and control circuits, and image signal processing to fix the color and all those kinds of things that you would expect to have. All that could be integrated on the chip. That's where we coined the phrase camera on a chip, because all that stuff was just on one chip. And that's what made the whole camera cheaper too.
So I was going to ask you, the improvement that we see year over year in video and image quality, is that due to more advanced chips? Is that due to more advanced software, taking the same information from an older chip and just making it better, or both?
Yeah, all of the above. So for one thing, the semiconductor industry for other purposes constantly improving the technology, so better microprocessors and memory chips and that sort of thing. And also, lower power and things like that. So Moore's law, which you may have heard of, which is the shrinking of microelectronics, is still there in the background today. Mm-hmm. So you get kind of a free ride once you hitch your wagon to the CMOS recipe. As the CMOS recipe improves, then you can also improve your product as well.
Here's a very random question that just popped in my head. Have companies like Apple, does Steve Jobs ever call you and go, "Hey, Eric, thanks. you made our company"?
Zuckerberg doesn't call me.
No. Okay.
Called me, but
you're forever the man behind the curtain, I guess, right?
It's okay. It's all right.
Yeah. Maybe that's not so bad. So we know where cameras, digital imaging, came from. We understand where it is today. I think it's an amazing technology today. Where's it going? it's hard to imagine it can get better, but we don't know what we don't know. So what in your opinion is the future of digital imaging?
Right. Yeah. By the way, I should mention, of course, even though we did the invention at JPL, and all the cameras today still use that ideas that were in our patents. The technology improved so much in the past years because of work of like thousands of engineers around the planet at all those big companies. It's not like me doing all the work or anything. So I sit back and enjoy the fruits of my labor, perhaps, but or fruits of their labor, I should say. But as we move forward, I think we'll see more things integrated on the chip, especially with a stacked wafer technology, where we can actually build multi-level wafers on top of each other. It's kind of an advanced packaging thing, but it allows for three-dimensional interconnects inside this wafer stack or chip stack, which can allow us to do more things right there on the focal plane with the image sensor. Also, we can start to use a lot more computational imaging. People use a lot of software now to improve images where they aren't even they're kind of guessing, like filling in things that most likely would have been there, but your camera didn't catch it for some reason, and using neural networks to kind of make a very, very likely guess as to cleaning up background noise or improving sharpness or improving the image in the dark, just computational imaging. So that's becoming more and more part of photography or videography or smartphones. And then we still have the same basic problem all the time, is like, can we make it more sensitive? Can we make the chip more sensitive so it can see practically in the dark? And that's one thing that I've been very interested in recent years myself.
I know your technology has gotten so miniaturized that it can now be swallowed in pill form. The medical industry uses imaging to capture images of the internals of a person. Is that correct?
Yeah, actually, that was one of the very early projects we did at Photobit in the late 90s. We worked with an Israeli group that had the concept. They were actually missile scientists that were trying to work on something that was non-military. And so they said, okay, well, let's put this like guided missile in a pill form and put it in into your digestive system, and we'll put a camera inside there and beam out through radio link images. We'll just take like a picture every second, and then the doctor can play it back fast motion and time lapse photography, and take this fantastic voyage through your intestines. And it's like one of the only ways to non-invasively see what's going on in your small intestine. Well, in case you were wondering, it's a disposable camera.
Yes. Yeah. No reuse. Right. Exactly. We talked about Photobit. You started Photobit after you left JPL. Photobit was the first licensee of the technology that you were involved with, the CMOS technology. Is Photobit still around?
No, Photobit. Well, of course, its descendants are around. Photobit was acquired by Micron in 2001, just as the smartphone camera was clearly going to become a market. Micron acquired Photobit, and then Micron spun that division out as a company called Aptina. And then Aptina was kind of a standalone again, kind of like Photobit, but bigger, stronger, smarter, perhaps. And then Aptina itself was acquired by onsemi, which is out of Motorola. Grew out of Motorola, and onsemi is still around. And On actually has an aggregate of a number of companies. The old Kodak CCD operation and CMOS image sensor operation eventually is acquired by On, a couple companies in Europe. Uh, and I still talk to those guys today, and some of my employees, my former employees at Photobit, are still in management positions at onsemi and other places too, including Apple.
Mm-hmm. You do have a history of coming up with creative company names. Photobit, Gigajot. What's Gigajot about?
Yeah, so Gigajot has to do with this low light sensitivity issue. So what if we could count light, one light particle at a time, called a photon, which is a really itty bit of light energy. But it comes in and lands on the image sensor chip like rain in our bucket before. But instead of measuring the bucket, why don't we just like count every raindrop that comes in one at a time and kind of digitally count it up? Could we do that? And that really means that you have to build a chip that's so sensitive that you can measure one electron, just one electron, and count it. If there is an electron that's generated by light, you get a digital 1. And if there is no electron, it's a digital 0. So you could have lots of tiny pixels. The vision is to have like 1 billion pixels on a chip. But they're very specialized. They're only like 0 or 1. Was there a photon or wasn't there a photon? And so we gave that special pixel a special name called a jot, which is Greek for smallest thing. And so Gigajot is, 1 billion jots.
1 million jots, yeah.
Yeah. And it actually works. We figured out how to do it with my PhD students at Dartmouth, which is, I don't want to pat myself on the back too much, but wow, it was one of those crazy ideas. I didn't know it was going to work, but it did work. And compliments to my students who helped make that work. And then when they were done and finished their PhD, it was like they wanted to start a company. So they picked up out of New Hampshire and eventually moved to where else but Pasadena, California. And that's where Gigajot is today. And it's still a small company, but I have to say they had to continue doing R&D a little bit to get it to commercial level, and now I'd say they're very close. So I expect to be the next growth phase soon.
Could this be the next CMOS? Changing the world?
No, I don't think so. I think, it'd be great. Lightning doesn't usually strike twice at the same place, but it'll be a niche market thing. You cannot do any better for low light sensitivity than counting every photon.
Right.
So for a lot of security applications or defense applications, or maybe even automotive or Internet of Things, for that niche market where low light sensitivity is really everything, and high resolution too, with 1 billion jots or something like that, it may fill that need. And who knows, maybe it could down in the future supplant my existing technology. But I think what will happen really is that they'll move together, and CMOS image sensors will adopt some of the things that we invented for we call the quanta image sensor, quanta light, quanta image sensor. So CMOS image sensors and quanta image sensors will kind of merge together and in a dual chip, perhaps.
You talked about your students at Dartmouth, which in the few minutes we have left, I want to talk about entrepreneurial studies. You are in charge of an entrepreneurial program, or I believe, at Dartmouth.
Well, so I'm
put it in the right framework for me.
Yeah. So most of the time I'm a professor of engineering, but a third of the time I have an administrative role as associate provost for entrepreneurship and technology transfer at Dartmouth. So that means I'm in charge of the technology transfer offices, all patents and licensing and all those kind of issues. And I'm also responsible for our Center for Entrepreneurship, or the director of the Center for Entrepreneurship, to be more exact, reports to me. And try to look at an integrated way of taking this technology that we develop at Dartmouth. And I think Dartmouth is a little bit unusual in our priorities, but my number one priority is to get that technology, which is really developed by public funding for the most part, and get it out to benefit society. And the best way to do that is to enable entrepreneurs, the inventors themselves, to go ahead and do it, because no one else has a passion like the inventor does for doing that. So whether it's faculty or graduate students, undergraduate students, we want to make that happen. So number one priority is to get technology out and benefit society. We have some pretty generous intellectual property arrangements with faculty and staff. And our number two, that's because our number two goal is to retain the best faculty and staff that we can at Dartmouth. And then number three is to try to make money along the way. So that's number three, though. So we can make money and sustain ourselves. That's also a very good thing.
I enjoy talking to entrepreneurial students. I've worked, every once in a while I'm invited to speak at one of our local Cal State universities, Cal State San Bernardino, and I've gotten to know and become friendly with their entrepreneurship program leader. And they have a gig there that I like to go to. It says, have lunch with an entrepreneur. It's basically speed dating. You're at a table for 10 minutes with 8 students about to graduate, and the entrepreneur changes tables every 10 minutes or so. So it's this round robin, and they pitch you. It's not a fast pitch contest, but they pitch you ideas, and they are just amazing. I mean, the difference, I think, between like an MBA program or just a business administration degree or something, and an emphasis on entrepreneurial gets real, not theoretical. It's from what I've seen, the whole concept of bootstrapping and overcoming objections and all the things that every business is faced with that is not always taught in other more formal studies is a valuable tool. And I love talking with people with ideas. Some of the ideas, you just have to the ugly baby picture. It's like, oh, cute. But some of the ideas are brilliant, and some of them are just ideas. But the fact that these kids have ideas is reassuring to me as I get older.
Yeah, well, another hat that I wear is we have a unique program at Dartmouth called the PhD Innovation Program, where we teach PhD students not only normal research skills and doing world-class research, but also how to commercialize their technology and business ideas. So kind of in that vein, and we've been pretty successful at turning out some really crackerjack students or graduates that hopefully will change the world in the coming decades. So that's a blast. I really enjoy that program a great deal.
So some departing wisdom, Eric, what advice would you give to budding entrepreneurs? And I ask that now, I think, because it's a more relevant question today than maybe ever before, because we think of entrepreneurs as young people, in their garage, living with their parents. But today, with all the stuff that's going on with the pandemic and all the knock-on effects of the pandemic, there's a lot of people that find themselves out of work and have had this idea in the back of their head for years that they now may have an opportunity. The door is open, to either go back to 9 to 5 or maybe do something on their own. So whether they're young or old, what advice would you give to someone that's got an idea and thinks they want to pursue it?
Right. So, I have so many things to say to that, but, one is encourage people to give it a try. Don't bet your house on it. Give it a try. And kind of do it on a shoestring for a while. And then don't be afraid to use other people's money to make it happen. Also, you have to give away some ownership, but again, I don't advise putting your house at risk if that's the situation you're in. Also, I'd say don't give up right away. If it doesn't work the first time, it may take a number of tries to perfect your idea, or pivot, as they say sometimes. But also, sometimes it's like cards, right? You have to know when to hold them and when to fold them. So at some point, maybe the idea that you thought was the perfect idea isn't just not the right time, or you didn't have the right luck that you needed. The world's not ready for it. So you have to recognize that there are factors out of your control that may make it not right. But persistence is worth a lot.
Yeah, and I think also what I like to tell people is failure, in many things, failure is failure. I think in entrepreneurship, failure can be success, because if I was going to hire somebody that's had 10 businesses all successful versus someone that tried and failed, I part of me would want to go. I mean, the odds would say go with the guy that's successful or the gal that was successful, but part of me wants to at least learn more about the person who's experienced failure, because I think there is more to learn from failure than success. Success might be luck. Failure is usually either bad luck or a set of bad decisions that one can learn from. So I think that the great thing about entrepreneurship is that there really is no win and lose. Even in loss, there's a win somewhere, particularly if you're going to try again.
Yep, I agree. So, and I think that the time is more ripe than ever for entrepreneurial activity in the United States. So,
yeah, and particularly in the United States, I'm pretty well traveled, as I'm sure you are, and my parents are both immigrants, and although it's possible in many other countries, it's so much more difficult in many other countries. The obstacles are real; they're much larger in other countries than they are here. I think the United States is it's still in many ways the Wild West. Anything is possible, and maybe I'm saying this because we're recording this on election day. I don't know. Maybe I feel a little patriotic, but I do think that the United States is uniquely set up to allow people to pursue their dreams, and there are fewer obstacles. I mean, there's a gigabit of obstacles out there, but I don't think the government throws too many of those in. There's just real world obstacles. There's competitive obstacles.
The government does a lot to also try to help small businesses through like the Small Business Innovation Research Program, for example, at Tech. And it's helped my company, Photobit, a lot. And it's also helped GigaJet a lot. So,
yeah, the first building we purchased when we outgrew the garage and some smaller units, I was able to purchase a building through SBA, through Small Business Administration. I mean, they were there. We can say a lot of things about government interference and regulation and all that, but for small businesses in particular, they're there. And the whole supply chain, particularly government-funded supply chain, is set up to favor small business and minority-owned business and women-owned business and all of that. So, yeah, I agree with you. Take advantage of it. And I love the idea of using other people's money. I remember my first attempt at getting money. I actually wrote a business plan, took it to a bank, and they were kind enough not to laugh. And they waited 2 weeks to turn me down. I'm sure it was 2 seconds, but they waited 2 weeks to mail the letter. And, and then you do what you got to do after that. But yeah, I agree with your advice there. So, Dr. and Professor Eric Fossum, thank you so much for being my guest today. I really enjoyed this conversation a lot, and I'm sure my audience will as well.
Great. I enjoyed it too. So thanks again for inviting me, and thanks for spending some time with me.
Well, thank you. Well, that's another episode. Thanks for listening to the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on iTunes, Spotify, iHeartRadio, or wherever you get your podcast. Reliability Matters and other reliability-based podcasts are available at Circuit Assembly's PCB Chat at pcbchat.com and at Ascendo Reliability at reliability.fm. Thanks for your comments. Please keep them coming. Send comments and episode suggestions to Mike at mikeconrad.com. That's Conrad with a K. Until next time, thanks for listening and keep doing it right.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.